Thank you. So before I start, of course, I would like to thank Sophie and Marius and Yuri for the invitation. So I'm going to tell you about a joint work with Sophie. So I have to thank Sophie twice, actually. And okay, so I have to explain what I mean by an ergodic operator. So this does not mean mean ergodic. So the definition is like this. So you start with a topological vector space, Polish, and I will say that an operator is ergodic if it admits an ergodic probability measure with full support. So this is my definition, not at all an official definition. I mean, usually people, when they think of an operator and they say ergodic, I believe most people think mean ergodic, so this is not at all the same thing, okay? These operators have dense orbits, so I mean, it's not at all the same. So full support means that every open set has non-zero measure. And what I would like to try to explain to you is how you can see that an operator is ergodic or is not ergodic. So this is this was the introduction. Okay, so there will be 3 parts in the talk, and the first part has to do with frequent hypercyclicity. So you all know the definition now of a frequently hypercyclic operator. Anyway, I would like to introduce a few notations. So assume you have your operator T, and you take a point in the space and a set in the space, and I will denote by n sub t of x and v. So this will be a set of integers. This will be the set of all integers I, such that ti of x falls in V, okay? I will use this notation more than just one time, so it is better to write it down. So now, what does it mean for an operator to be FHC? And I will say FHC because it's hard to me to say hypercyclic, so and I just say HC for this word. And so if you can find a point in the space such that whenever you take an open set, then this set here has positive lower density. So I think it's not necessary to recall the definition of lower density of a set of integers. So this is the definition. And now what is clear from the definition is that if you are ergodic, then you are FHC. I just recall you how it is proved. So if you take an ergodic measure with full support, then in fact, mu almost every point of the space satisfy this property which is written in brown, more or less, yeah, okay. And this is quite easy to prove. This follows from the point was ergodic theorem, so okay. So now, it would be nice, actually, if the converse would be true, but as you will see, this is not true. The converse is not true in, at least on some Banach spaces. It may be true on some nice spaces, but this we don't know. And so now, let me introduce another definition. So let us say that an operator is FFFHC, okay, so with free F. It's a kind of joke. I mean, I didn't have a very intelligent name for this notion, so this is just a joke. So if what? If there is a point in the space such that it starts in the same way, if you take any open set and you look at this set, nt of x 0v, and then you translate by some integer, and you take the union r from 0 to some other integer n, and you look at the lower density, and you take the limit as n goes to infinity, and this should be 1 this time. Okay? Okay, so this is a definition, kind of, I mean, formal definition more. I mean, but you will see that after all it may be interesting. And so now, of course, FFFHC implies FHC. And now our first result goes like this. So you assume, okay, X is a rather nice Banach space, so it is a reflexive Banach space. And unfortunately, you assume that your operator is invertible. Actually, I don't know if the result is true if you don't assume that T is invertible, and that's sad in some sense, but okay. And now the result is that, in fact, it is ergodic exactly when it is FFFHC. This is if and only if. So at least formally, this is a nice result. Now, of course, if you remember the introduction, this is not such a nice result because it doesn't seem to be very effective. By this I mean that how do you check this FFFHC property? This does not seem to be quite obvious. Anyway, this is a result. I mean, this is a general result. And the other remark is that if you just assume that T is FHC, so with just one F, then, okay, and here you don't even need the T to be invertible, then you will always have an invariant measure with full support. So perhaps this measure will not be ergodic, and this is the point. I mean, but with the classical notion, you always get an invariant measure with full support. This will be more or less clear from the proof that I will outline in a few minutes. So, and in fact, you can have a characterization of this property. An operator has such a measure if and only if a weaker property than FHC holds, and it goes like this. If you take an open set, then you are able to find a point which is allowed to depend on the open set, such that the lower density of this usual set is positive. And this is again, this is if and only if, so which again is nice. And actually, you can replace lower density by upper density, and this is the same. So this is the first result. And okay, I would like to give a sketch proof of this theorem as it is stated. Okay, so let me just erase what is not necessary and okay, so proof. Is it okay? Can you read? If it, I mean, is it large enough? Okay, so if you allow me, I will not prove the only if part because it is more or less the same proof as the proof that ergodic implies FHC. So this is just the ergodic theorem. Okay, let's say this in this way. Well, you have to write down perhaps not one line, but 3 lines to prove this implication using the ergodic theorem. So what about the if part now? So you have your point here. So this is a FFFHC point for T. And I have to introduce some notation. So I will denote by K the family of all weakly compact subsets of X. So, since you are on a reflexive space, you know that you have a lot of such sets. And another notation, maybe I don't know, maybe I go there. So I will fix an invariant mean on L infinity. Okay, and so this is a linear functional on L infinity, such that m of 1 is 1, and m of, okay, this just means this. Okay, and m of 1 is 1. Okay, and well, instead of writing this, I will write because after all, any such mean is a finitely additive measure on the integers. So I will emphasize this and write this in this way. Okay, so this, I think it's, I mean, in a sense, more natural to write it in this way. And, okay, so now what do? I erase a part of the black. No, I don't need to erase. And now I will define first, for every weakly compact set, I will define something, which is a measure. So for any weakly compact set, you will have a finite measure, finite Borel measure, on X, such that the following holds. So if you take any function which is continuous on K for the weak topology, then the integral of f. So this new K will be supported on K. And this will be like this. You take this, you look at this. Of course, this means nothing because f is just defined on K. So you add the indicator function of K. And you average over the mean. Okay, so this is a definition. Obviously, this does define a Borel measure on K for the weak topology, but the weak topology and the norm topology have the same Borel sets because you have a separable space. So you can view this measure as a Borel measure on X, which is supported on K. And okay, this is it. And what I forgot to write here is that I assume that my mean satisfies this, that okay, so okay, so this is a definition of a measure. Okay, so what do you know? What is clear is that this is a finite measure because nu k of x, which is also nu k of k, you just get it by taking f equal to 1, and so this will be not greater than 1, obviously, because this is like this. And now you define something which is this is here. So you just define something which is called nu. So for any Borel set A, you just declare that nu of A is the supremum over all weakly compact set of the new K measure of A, okay? And so what you have to check now is that first, this does define a measure, which is not difficult to prove, so and moreover, it is an invariant measure. And okay, this is not completely obvious because here, this is on purpose that I took a mean on the positive integers. So if I would have put z here, it would have been more or less obvious that this is indeed a measure. This is indeed T invariant. Here, in fact, I put n because for this part of the proof, it is not necessary for T to be invertible, in fact. So this is the point. So I put n really, but still, this is an invariant measure. And of course, it is a finite measure. And okay, so now if we don't assume that T is invertible, then it would be quite easy to get that this measure has full support. But now I will need more to conclude the proof. So, how does it go? I have to be a little bit careful. So, what is it? So, okay, let us take an open set, V. Okay, and now you can put in it a closed ball, which is, of course, weakly compact, because you are assuming that your space is reflexive. And now, since T is invertible, so you take also any n, then since T is invertible, then this implies that if you look at this set, so this is still a weakly compact set. Okay. Okay. Now, what do you do? Well, you look at the measure of nu of this set, or if you prefer this set, but okay. So, of course, this is at least and by the definition of your measure, this is at least equal to this. Okay, and now, by definition of what new something is, this will be at least equal to, there is no limit, sorry. Yes, there is a limit. No, there is a lower density of this set. Okay, so this is it is just the definition of what new k is. I erased the definition of new k, or of new something, but this just follows from the definition. But now, what is this? This is just this set, okay? Because this is an immediate consequence of the definition. So this goes to 1 as n tends to infinity. So this is the point. Okay, so what do we get? What we get is that if you take any open set, well, you have that the measure of this set is equal to 1. Okay? So now you take a countable basis of open set. And what you have now is that, in fact, and you take the intersection of all these sets over K, and this will give you exactly the set of points with dense orbits. So what you get is that the measure of the hypercyclic vectors of T is equal to 1. Okay? So I don't say that nu is an ergodic measure, but now you apply the ergodic decomposition. And this gives you an ergodic measure such that the measure of this set is non-zero. And this condition implies that, in fact, it has full support. Okay, so can you still read here? Okay, it's better in this way. Okay, so this was more or less the proof of the first theorem. And okay, it's time to continue. So let's continue. I'm not cheating. I mean, it's more or less a foolproof. It's not very hard to prove. I mean, but okay, there are some details, but this is more or less a foolproof. Okay, so now I pass to another topic, a completely different topic, apparently. So I will say a few words about unimodular eigenvectors. So what do I mean by that? So this time X is a complex vector space, so we don't have a real version of the results here. And so what is a unimodular eigenvector for T? So this is simply an eigenvector whose eigenvalue has modulus 1. Okay? And the set of all such vectors I will denote it by E of T. I don't know why E, but oh. Okay, and if you take any vector here, I give a name to its eigenvalue, and this will be lambda of x, which is not surprising. Okay. And okay, so these are the notations, and now a second nice result goes as follows. First, a definition. So you will say that E of T is perfectly spanning. This is what Quentin told us about on Monday, but okay. Anyway, I talk a little bit about this now also. So if the following holds. So if you take any countable set D in the circle, and you look at the eigenvectors whose eigenvalue does not belong to this set, so you remove. After all, it may be quite a big set of eigenvectors. Okay, still countable, but I mean the number of eigenvalues is countable, but still the set of vectors may be big. And if you remove this countable set of eigenvalues, then you still have enough to span the whole space. Okay, so this is the definition. And now there is a. So what does it mean? Is that really you have a lot of eigenvectors and of eigenvalues. This is the point, because of course, if you take the identity, then the eigenvectors span the space, but if you remove just one eigenvalue, then you don't span nothing. So, okay, so the second result is like this. If E of t is perfectly spanning, then you are ergodic. So what is, what is really nice with this result, I think, is that you don't assume nothing on the space. This is, this result is a kind of end of story for a story that began quite some time ago. But at each stage, there were results of this type, but assuming something. Something on the space or something on the way you can generate the eigenvectors. But in fact, you don't need to assume nothing. So this is the point. And some remarks before I try to give a sketch proof of this theorem. So the first remark is that, in fact, you can do better than this. You can not just get an ergodic measure with full support, but in fact, you can find a Gaussian measure, which does the job, at least if your space is locally convex, because otherwise I don't really know what is the correct definition for a Gaussian measure. But anyway, this is true, and you also have a similar result for mixing. I will not go into details for this result, but in fact it is exactly the same, except that you replace the countable sets by something else. Okay. So this we proved with Frédéric, and it appeared last year, but it was proved a little bit before, of course. But, and last remark, perhaps, is that if you are on a nice space, and if you require that your ergodic measure is Gaussian, so if you're on a Hilbert space, for example, then in fact, this is an if and only if. That is, you're ergodic in the Gaussian sense if and only if E of t is perfectly spanning. So this is another point. And the second remark is that unlike the first theorem, this one is extremely effective. It is really easy to check if your E of t is perfectly spanning, because what you have to do is just this. It is enough to find a family of eigenvectors, maybe, okay. The family is parametrized by a perfect subset of the circle, and you have to assume, okay, that the eigenvalue of E lambda is just lambda, that the E lambda depends continuously on lambda, which usually is more or less obvious, and that they span the whole space. And if you have this, it is more or less immediate that you have perfect spanning. And this is extremely easy to check. So to give just one example, yeah. If you, let's say, to be on a non-Banach space, so if you take X to be the space of all entire functions, and the operator is just the derivation, okay, quite a simple operator, then you just put E lambda of z is the exponential, and this works perfectly well. It's just, and in most cases, it is not really harder to check this perfect spanning property. So, okay, so this is the theorem, and now the story of this theorem is rather funny because, okay, we had a proof. Actually, Frédéric had a proof which appeared in our John paper, and Sophie, a few years before, also had a proof, but she didn't realize that she proved this result, in fact. And so, stated in this way, with the Gaussian measure, it's not clear that. But anyway, both proofs were rather technical in some sense. There was a part which was, for the Gaussian case, there was a kind of automatic part. There is a Gaussian machinery which works quite well. But at some point, you had to fight to get something non-trivial, and it was quite technical. What I would like to do now is to outline a soft proof of this result. So I just erased this because I moved the blackboard up. So it will be a really short sketch because time is passing. So sketch proof, or so how do you do this? So again, I need some notation. So I will denote by P of x the set of all Borel, sorry, this is Borel was French after all. So, okay, and okay, so this is this you endow it with its usual topology, which is the weak topology of measures. Okay, so this is a Polish space. This is what I just want to say, and you denote by Pt of x the set of all t invariant measures. So. Okay, and now K of x will be the set of all compactly supported. And of course, Kt of x is what you guess. Okay, one point is that this set is not empty because you have a fixed point. 0 is a fixed point of t. So okay. And the last notation is that I will denote by OT, O sub t, the family of all open sets O, such that t minus 1 of O is contained in O. Okay? So, too many notations anyway. Once you did this, you have finished the proof. So, the key lemma is like this. So you take any O in this family of open set, and you look at Kt of O, which is the set of all mu in Kt, which are supported on O. Okay? Then, in fact, this set is dense in Kt of x. Okay, so this is not quite obvious. This is the key lemma, but if you have this, then this is okay because so now what do you do? What you observe first is that, well, if you look at the set of all hypercyclic vectors of T, then this can be written as a countable intersection of open set OK with OK in this family of open sets. You just define the OK like this, where Vk is an open basis for x. Okay, and so now what I should add here, that kt of O, sorry. What I have to add here is that this set is dense, but it is also G delta. And this is easy. Okay, this is very easy I mean, it's not part of the lemma. What is part of the lemma is this, but I remind you that this is also a J delta set in the weak topology. And so what you get here, if you apply the Baire category theorem in, okay, the closure of kt of x, then you get that you have an invariant measure such that, which I should call nu, such that the measure of this set, hc of t, is equal to 1. And then you apply the ergodic decomposition as before, and this gives you that t is ergodic. Okay, so as written, it is trivial, but of course you have to prove this, which is the technical part. So how do you prove this? I will not do that, but I'm not sure I have time even to outline the proof of this. So, okay, maybe I will not write anything. How do you prove this? In fact, of course, this is here that the perfect spanning property is used. And in fact, the kind of measures that you, okay, sketch proof of lemma. So the step one is this, that in fact you are able to find a family of measures in this kt of O, which goes to the point mass at 0. Okay, and what kind of measures are here? In fact, they are like this. They are the distributions of, okay, so what is this? So theta I is a random variable uniformly distributed on T, and the xi are eigenvectors of T, unimodular. So obviously any such measure is an invariant measure, so what you have to do is that if you are careful, then you can manage that you can find the vectors here in such a way that they are in the set here, or I mean, the measure is supported on the set here, and they go to the point mass at 0. And this is, of course, here that you use the perfect spanning property in a way which is not that terrible, but you have to be a little bit careful here. You have to do something. In fact, what you do here is more or less the very first part of Sophie's proof of the theorem. I mean, so it is so in fact what we did here is just to say that this very first part is enough to get the result. This is so if you are lazy, just use the Baire category theorem. This is nice. Okay, so I think it's enough for this this result. So maybe a very short interlude because okay, so this will be quick, but because I'm afraid I'm running out of time. A small remark about this perfect spanning property. So if you have an operator T, then in fact this perfect spanning property is equivalent to what follows. So you can find a set E, a set of unimodular eigenvectors, which spans the whole space, and such that if you take any U in this set E, then you can find other vectors in the same set which are close to U, but which don't have the same eigenvalue. This is the point. So this is equivalent to the perfect spanning property. And so, for example, if you assume that the periodic points are dense, and that any periodic eigenvectors can be approximated by periodic eigenvectors who don't have the same eigenvalue, then you have this perfect spanning property. So this does not seem to be extremely strong. I mean, how could this be done true? I mean, if you have a lot of periodic vectors, then, well, you move a little bit and this will be still okay. But so it is very tempting to believe that the following is true. That if you are chaotic, which is hypercyclic with a dense set of periodic points, then in fact you have this perfect spanning property. And so you are ergodic, and so you are frequently hypercyclic. But this, you know, is not true. This is what Quentin showed us on Monday. And I mean, it is an extremely nice result. But just from this point of view, it is also quite surprising. I mean, that this is just, I wanted a kind of advertisement. Read Quentin's paper. Okay, so this is my interlude. So now I pass to the last topic. So I'm going to introduce some kind of parameter which is associated to any operator. So this time you are in a Banach space. You could do this on any space actually, but you would have to change the definition. But so you take a hypercyclic operator T, and you define this C of T. You look at this time the upper density of sets of this form, where the open set is an open ball centered at 0. Okay, so BR. Maybe I should write this. So you look at such quantities, and you take the supremum over all hypercyclic vectors, and then the supremum over all R, and this is C of T. Okay, this is the definition. Why not? And so what can you say of this C of T? So obviously, this C of T is greater than any upper density of any such set of any set of this kind. But on the other hand, what you can prove is that in fact you can. I mean the radii are in fact not important. That in fact one can show that there are lots of vectors such that, in fact, if you look at the upper density of nt of any ball, this is equal of C of T for, in fact, any ball. I mean, the radius has, in fact, nothing to do in that business, and almost all points are maximal in this sense. Okay. And last remark, which actually is not useful, but anyway, it's obvious, is that if you are FHC, then obviously your C of T is positive. But in fact, you don't use this in what follows. Okay, so why introduce this? So just a small parenthesis. So one example of use. So assume that, okay, you have this Omega set from the previous slide, such that the upper density of nt of x B1, this B1 is the unit ball, is equal to C of T for every x in this Omega set, okay? So now you take an open set, which is like this. So, okay, maybe it's better to draw a picture here. So you have B1, which is here. You have V, which is here, and B, okay, this will not be okay. So V is small, and B2 is here. This is the picture, okay? And so now what can you say? If I then look at, take any point in G, then look at this upper density with B2, okay? The large ball. So this is, of course, at least equal to the sum of the upper density with B1 and the lower density with V, because these two sets are disjoint. But the first one is equal to C of t, okay? And on the other hand, what you have on your left is not greater than C of t, just by definition. So the only possibility is that, in fact, the lower density of nt of xv is 0. I mean, for any v. So this means what? That no vector x in this co-omega set can be a frequently HC vector for t. And so in particular, the set of all frequently HC vectors is always meager in the space, which is in complete contrast with the fact that the set of points with dense orbit is co-meager, actually dense G delta. So this is just one example to explain you, or to convince you that this parameter may be useful. And so this result was proved by Mutatu and Frédéric and Imre Ruscha. And I am pretty sure that other people do this result. I mean, but anyway, this is true. And this proof is in our paper with Sophie. Okay, so now I state a lemma. Yeah. So the lemma is like this. If you take any HC operator T, then you have a co-omega set of vectors X such that this happens. You iterate T, so Ti of X goes to 0 as E goes to infinity along some set which has positive, I mean, which has upper density at least C of T. Okay, this is the... So as stated, this may be wrong actually. I mean, maybe you should assume that C of t is positive, because anyway, if C of t is positive, this is clearly true. Let's say this is true, like this. Well, this, because if you just assume you have HC, you may have no orbit going to 0. So, okay, so this is... Well, you still assume that you go to 0 along some set. So I has to tend to infinity. So, I mean, this is true, of course. Well, yes, you have an infinite set. Okay, so this is correct like this. Okay, even if C of t is 0. Anyway, and how is it proved? It is just obvious. It is the same set as before. I mean, the set G is the set of all x such that the upper density of nt of xb is equal to C of t for any ball. So this vectors x works. It's not very difficult to prove that. So now I state a theorem, which I will not prove, and that if you are ergodic, then in fact your C of t is equal to 1. Okay, so it is not only positive, it is equal to 1. And okay, this theorem is not very hard to prove, but what I would like to prove in the last 2 minutes, is it okay, 2 minutes, yeah? Do I have 2 minutes? So I would like to prove the following corollary, is that there exists FHC operators on C0 which are not ergodic. This is what I would like to prove now. So, in fact, we did not find the operator. The operator was already in the... He already existed. It has been constructed by Frédéric and Ruscha. And so there exists an operator T on C0 such that I forgot what what it satisfies. For some set A with positive lower density, is it correct? Yeah. We have that for any I in A and for any x in C0, the norm of Ti of x is at least equal to the first coordinate of x, okay? And so now what happens? So this can be done. I mean, it is not at all trivial that such operators exist, but once you have this, you see rather easily that, in fact, such a T cannot have, okay, T on C0, such that T is FHC, of course. This is the point, and it satisfies this. But it is very easy to see that such an operator cannot have C of T equal to 1. This is because of the lemma, in fact, because, I mean, it is a 3 lines proof to... Because, in fact, any set X, okay, if you take any set X in your set G above, which is not, I mean, there, okay, this is the set of the lemma. If you assume this, then you will have that the first coordinate is 0. And so, in fact, this set G cannot be dense. So this is the point. Yeah, this is okay, and I'm not sure I'm quite clear here, but because it's time to stop, so I'll just make 2 remarks. That the first one is that we do not know if you can do this on other spaces. And in particular, on reflexive spaces, we do not know if it is possible to do that. And the second remark is we do not know either if there exist FHC operators which has no invariant measure with full support. So I do not say ergodic, but this we have no idea, in fact. The main trouble is that we have no criterion to show that you have no invariant measure with full support. For ergodic, you have the C of T, which is nice, but for just an invariant measure, we don't know. So I think it's time to stop. I had a list of questions, but okay, let us forget the questions. And thank you very much.